Hello, class. Today we're going to learn about Newton's law of motion. Before we begin discussing Newton's three laws, we must first understand the concept of force. Force is basically a push or pull acted on an object. An object at rest needs a force to get it moving or change its velocity. Other forces other than push and pull could be weight, tension, friction, spring, and centripetal force. In this video, we'll discuss the force caused by push, pull, and weight today. Newton's first law states that any object at rest or moving at a constant velocity in a straight line will continue at the state until the non-zero net force acts upon it. The non-zero net force is included in the first law because two equal forces acted on an object in such a way could not change its velocity. So the object will still be at rest or still move at a constant velocity. The term inertia means resistant to movement. Object won't change its state unless a non-zero net force acts upon it. Before we continue with Newton's second law, we must first understand the definition of mass. A basic definition of mass is the amount of stuff in an object. Mass is not the same as weight. Weight is a force that accounts for gravity. So the weight of an object on Earth will be different than on the moon, whereas mass will always be the same, no matter if the object is on the Earth or out in space, because its quantity of atoms inside an object is inside of object. Recall that the inertia means resistant towards movement. Well, if you think about it, mass measures the inertia for an object. The greater the mass of an object, the harder it will be to push the object because there is more resistance due to the mass. Thus, the greater inertia means greater the mass of an object. The SI unit for mass is kilograms. Alright, now that we understand mass, we can continue on with Newton's second law. The second law is essentially the equation of sum of the forces equals mass times acceleration. In Newton's words, to describe this equation is acceleration is proportional to force and inversely proportional to mass. That sum symbol you see in front of the force is important to include because there could be more than one force acting on an object. Thus, we must add all the forces acting on an object to have it equal its acceleration times mass. If you notice on the previous slide, force is a vector, just like acceleration is a vector. So that means force has magnitude and direction. The unit we use for force is named after Newton. We use the letter capital N to indicate the unit for Newton. So instead of writing kilograms times meters per second square, we can just write the letter capital N. Thus, the unit for Newton equals kilograms times meters per second squared. For our first example, we'll estimate the net force needed to accelerate a 1,000 kilogram car at half g, or half the value of gravity, and do the same for a 200 gram apple. First step is to calculate the acceleration at half of gravity, which is 9.8 divided by 2 to give us 4.9 meters per second squared. Then applying Newton's second law, sum of the forces equals ma, we just plug and chug to get 4,900 newtons. In part B, the acceleration is the same value, but the mass is much lighter. Please take note that the apple's mass is in grams, not kilograms, which is the SI unit for mass. Again, plug and chug with a mass of 0.2 kilograms to get 0.98 newtons. If you didn't notice, it takes more force to accelerate a car than an apple. Imagine that. Alright, next example. What's the average net force that is required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour within a distance of 55 meters? Just like we did with kinematics, we want to list our givens and finds and which equation to use. In our new chapter, we're using Newton's second law. Our mass is 1,500. Our final velocity is 0 because we're coming to a stop. Our initial velocity is 100 kilometers per hour. Our final position is 55 meters, so we'll assume our initial position is 0. And our equation that we're going to use is sum of the forces equals ma, because we're trying to find what the average net force is, which is sum of the forces. First, we want to change our initial velocity to the correct SI units of meters per second. So we have 100 kilometers per hour. We're going to multiply that by 100 meters over 1 kilometers, and multiply that by 1 hour over 3,600 seconds. The appropriate units cancel out, and we end up with 27.78 meters per second for our initial velocity. So I'm just going to replace our initial velocity with 27.78 meters per second instead. We don't have the value for acceleration. How can we find acceleration? Correct. Use a kinematic equation. The kinematic equation we'll use to find acceleration is v squared equals v squared naught plus 2a times x minus x naught. The final initial position cancel out because the values are 0. Now our equation is reduced. Then just rearrange the equation to solve for acceleration. Now just plug and chug to get negative 7 meters per second squared. Notice that the acceleration is negative. Does this make sense? Yes, because the car is slowing down. So the acceleration must point in the opposite direction of velocity, which the car is moving in the positive direction. Now we can just plug and chug in the force equation to obtain the average net force of negative 10,500 newtons. All right, now on to Newton's third law. Any force exerted on an object has an equal and opposite reaction. So if you punch a wall, the force into the wall will be the same amount of force the wall exerts on your fist, but in the opposite direction. Keep in mind, when thinking about the third law, the forces are on different objects, not on the same object. So in this example, shows a force on the wall caused by the skater and the force on the skater caused by the wall. A really cool example of Newton's third law is a rocket launching. The gas exerted out caused by the reaction of the rocket to propel upward. In exercise C, we have a tennis ball that collides head-on with a more massive baseball. Which ball experiences the greater force of impact? Both balls experience the same amount of force, but in opposite direction. Now, which experiences the greater acceleration during the impact? The lighter tennis ball, because if both balls have the same force value, which is F, then a tennis ball must have a greater acceleration, which is A, if the mass, which is M, is smaller according to the equation of F equals ma. Now, which of Newton's third law are useful to attain the correct answers? I would say mainly Newton's third law, but we also apply Newton's second law. Now that we've gone over Newton's three laws, let's go over the type of force known as weight. Weight is a force on an object due to the acceleration of gravity. The vector of weight always points towards the center of the earth. So since the acceleration for the force of weight is gravity, we can substitute g into a to get our equation for weight, which is Fg equals ma. Often I will only refer to weight as mg. Hopefully this equation makes it clear why mass is not equal to weight. Know that mass of an object does not change depending on its location. However, the weight of an object does. If an object is on the moon, it will have the same mass but different weight than on Earth, because the acceleration of gravity is different on the moon. Now, according to Newton's third law, every action has an opposite and equal reaction. Here we have the force of weight acting on the surface. The surface gives a reaction equal to the weight, but in opposite direction. We call this force caused by the table the normal force. We define the normal force always perpendicular to the surface. The variable we use is Fn. The arrow you see drawn on Mr. Lincoln is a rough sketch of what we call a free body diagram. We'll further discuss how to draw a free body diagram later on in this video.